Welcome to the GeoMethod channel. Today we are solving another interesting geometry problem. Here is today's challenge. Can you find area of the triangle? Take a moment to study the figure. Then, let us uncover the key geometric ideas that make the solution click. Here is triangle ABC, drawn with vertices A, B, and C. We are told all three side lengths, and our goal is the area of the whole region ABC. Side AB is the square root of 3. Side BC is 3 times the square root of 3. Side AC is the square root of 30. Every side is written as a radical. When every side is a square root, squaring is our friend, because squaring a square root just returns the number inside. So let us look at the squared side lengths. In decimals, the sides are about 1.7, 5.2, and 5.5. Side AC is the longest, and that matters because a right angle, if there is one, always faces the longest side. The angle across from side AC is the angle at vertex B. So if this triangle hides a right angle, it must sit at B, with segment AB and segment BC as its two legs. The converse of the Pythagorean theorem tells us the triangle is right exactly when the squares of the two shorter sides add up to the square of the longest side. That is the test we will run. Write the test for our triangle. We ask whether segment AB squared plus segment BC squared equals segment AC squared. Let us build both sides of that equation piece by piece. Start with leg segment AB. The square root of 3 squared is simply 3. That is our first squared length. Now, leg segment BC. 3 root 3 squared means 3 squared times root 3 squared, which is 9 times 3, or 27. That is the second squared length. Add the two squared legs together. 3 plus 27 gives 30. That is the entire left side of our test, coming from sides segment AB and segment BC. Now the right side of the test. Square side AC. The square root of 30 squared is exactly 30. Keep that number in mind. Compare the two sides of the test. The legs gave 30, and the longest side gave 30. They match exactly, so the converse condition is satisfied. Our first insight is this: the side squares reveal a right angle. So sides segment AB and segment BC are the two legs of the right triangle, and side AC is the hypotenuse. This naming is exactly what we need for the area. Because legs segment AB and segment BC meet at 90 degrees, one leg can serve as the base and the other as the height. No extra altitude has to be drawn. The area of a right triangle is 1/2 the product of its two legs. So the area of ABC is 1/2 of leg segment AB times leg segment BC. That is the whole plan. Put in the lengths. Leg segment AB is root 3, and leg segment BC is 3 root 3. So the area is 1/2 times root 3 times 3 root 3. Handle the radicals first. Root 3 times root 3 is just 3. The square roots cancel completely, leaving a clean whole number. Now bring back the extra factor of 3 from 3 root 3. 3 times 3 is 9, so the product of the two legs is 9. Finally, take 1/2 of 9. Half of 9 is 9 over 2. That is the area of triangle ABC. As a decimal, 9 over 2 is 4.5 square units. It is comforting that 3 radical sides collapse to such a tidy value. A second insight now finishes the structure. Heron's formula confirms the same area. So the area is 9/2. Heron's formula can be proved by dropping an altitude to side C, using the cosine law projection x equals a squared plus c squared minus b squared over 2c, substituting into k equals ch over 2, and factoring k squared into s times s minus a times s minus b times s minus c. That completes the solution. A good geometry problem often has more than one beautiful solution. If you see a genuinely different construction, a high-level idea that leads to another solution, or a thoughtful adaptation of an existing method, share it in the comments. Even a rough idea is welcome. A sketch of the key move is enough. We greatly appreciate these contributions. With your permission, we may feature the approach in a future Viewer Solutions episode and acknowledge you by name or channel handle. Thanks for exploring geometry with GeoMethod.